Good afternoon, everyone. So, in the previous lecture, we have discussed about five different immediate mode or online task scheduling algorithm, which are applicable not only for cloud computing, but it is also applicable for grid computing or also seen in parallel distributed computing. So, in order to simulate these algorithms, if you want to write the code for these algorithms, some standard data sets are available, and these data sets are having different size. One of the popular data set size is 512 into 16. So 512 represents the number of 512 is nothing but the number of tasks, and 16 is nothing but the number of meshes. Okay, or you can consider number of VMs, or you can consider number of clouds as per your requirement. So if you go for this particular data set, that is 512 into 16 data set, you will see these data sets having 12 different instances. The total number of instances is 12. Okay, and how these data sets are actually generated? These data sets are actually generated using uniform distribution. In mathematics, you have studied about uniform distribution. There are other distributions also you can use if you want to generate your own data set. But uniform distribution, the in this distribution, the probability distribution with equally likely outcomes. Okay, and you can use other distribution, but this data set actually used uniform distribution. Other authors also used some other distribution, and also the data sets is also very popular data set. So if you see, there are 12 different instances, and these instances are categorized into three different types. So you can see in this slide the name of the 12 different instances. They are categorized into three parts. Like you can see the first letter of each and every instances, that is U. Okay. First one is U. U stands for your uniform distribution. Then these instances are divided into, you can say, uh, these instances are divided into three parts, as I said. One is, you can see in the first four instances, the second one after underscore, we have C. C stands for consistent. C stands for consistent. Here I stands for inconsistent, and S stands for semi-consistent. So 12 different instances are now categorized into three different parts: consistent, inconsistent, and semi-consistent. Then what do you mean by actually consistent? In order to know that, let us take a very small example. Suppose you have taken, let's say you have taken four different tasks, T1, T2, T3, T4, and you have four different clouds, C1, C2, C3, C4. So basically these instances are nothing but a matrix, right? Matrix means it is of size 512 into 16. Okay. Matrix means this is of size 512 into 16. So if you look into this matrix, if you open this particular matrix, if you look into especially consistent matrix, you will see a structure like this. Suppose it is 10, it is 20, this is 30 and 40, and this is 5, 8, 10, 12. This is 23, 32, 43, 54, 70, 80, 90, and 92. So if you look into this particular matrix, this matrix is called as your consistent matrix. So what do you mean by actually consistent matrix? Consistent matrix means for a particular task, if one of the cloud is better, like if I ask you for T1, which cloud is better? then you will see their execution time is 10, 20, 30, 40 in 4 different cloud, C1, C2, C3, and C4. And you have seen that here the minimum time is 10. Assume that the ready time is equal to 0. Then you can say, yes, task T1, which is going to be assigned to C1. C1 is the best cloud for it. If you assign to any other cloud except C1, then it is not beneficial, right? But if you look into T2, T2 case also C1 is the best cloud. T3 case also, if you look into, this is a also the first cloud. T4 case also, it is the first cloud. So what I can conclude, if a particular cloud, let's say C1, is best for T1, then it is also best for all other tasks, that is T2, T3, and T4. Similarly, you can say, if I say this one, right? C2. C2 is the second best for T1, right? After C1, which one is the best one? The best one is C2 for T1. So if it is best for T1, second best for T1, then this cloud is second best for T2, T3, as well as T4. That is 8, 32, 80. These all are best for second best. C2 is second best for T2, T3, and T4, and so on. Right? So such type of matrix is called as a consistent matrix. That's why here you can see the letter it is written here is C. C means consistent matrix. That's why I told you while we were discussing K% based algorithm, I told you, suppose K value is 50%, then you will take 50% of the machine. So in consistent matrix, identifying the 50%, like in this 4 cloud, which 2 cloud is best, that you can easily determine in the case of consistent matrix. But inconsistent matrix, determining this require the execution time of the whole in all the cloud, execution time in all the cloud. Then only you will come to know which one is the best one, which one is the second best one, or so on, right? There is another matrix here you can notice that is called as I, which is called as inconsistent. For example, if you take a matrix like this, I can tell this is 10, 20, 30, 40. That is nothing but task T1 time in C1, C2, C3, C4. But when I go to T2, I found that this is 5, this is 8, this is 10, and this is 12. And for T3, you can say it is 43, 54, 23, 32. And for T4, you can say 70, 80, 90, and 92. Right? So if you look into this particular matrix, which is an inconsistent matrix. Why it is an inconsistent matrix? Because for the task T1, which cloud is better? Then you will say the least time is taken in the C1, then it is better. But if I ask the same question for T2, then you will say C2 is better. If I ask for T3, then you will say that C3 is better. If I ask for T4, you will say C4 is better. So if a particular task is better in a particular cloud or a virtual machine or a machine, it is not necessary that it is better in other, that machine or that cloud or that virtual machine is better for other tasks. That we have seen here. C1 is best for T1, but C1 is not best for T2. Similarly, C1 is also not best for T3. So we can say that this is completely inconsistent matrix. So in this matrix, if you choose KPV, like K% best, then determining best to machine require the entire row to be scanned, right? You have to go through each and every element, then only you will come to know which two machine is better, which in fact require order of n complexity. There is another matrix here you can see that is called as S. S stands for semi-consistent matrix. Semi-consistent is a special case of inconsistent matrix. We says that in a inconsistent matrix, if you can say part of the matrix or a submatrix is consistent, then we call that as a semi-inconsistent matrix. Semi-consistent matrix. For example, if you have taken, like here I take 512 into 16 matrix, right? The data set consists of 512 into 16. So in 512 into 16 matrix, if you look into this matrix, it is a very huge matrix. Let's say I have taken these instances like us dot hi dot o. O stands for, it is the object file. That's why you can see O is there. O is padded with each and every instances, right? So in this 512 into 16 instances, if I can say a 256 cross 8 matrix, which is a sub matrix of this 512 into 16. 256 cross 8, which is a subset of your 512 into 16 matrix, right? Like if I take a 4 cross 4 matrix, you can say this part is a 3 cross 3 matrix. It is a sub matrix. Again, this is another 3 cross 3 matrix. Again, this is another 3 cross 3 matrix. Another, this is also a 3 cross 3 matrix. There are so many 3 cross 3 matrix. So if a submatrix is consistent, okay, it is an inconsistent matrix only. Semi-consistent is a special type of inconsistent matrix in which you can say part of the matrix is consistent. Like 512 into 16 matrix, if I can say you 256 cross 8, there is a matrix inside that which is consistent. And you know what is a consistent? Consistent means a particular cloud is best for everyone. Then we call that as a semi-consistent matrix, right? So in this way, we have 12 different instances. And if you write the code for OLB, MCT, MET, and the switching algorithm by taking the lower limit as 0.6 and higher limit as 0.9, and KPB by taking K is equal to 20%. So total M is equal to your 16. Total 16. I told you the 16 number of machines are there. So 20% of 16 means how many machines you need to consider? How many you have to consider? Tell me. 20% of 16. How much it is coming? 16 into 20%. So it is 3.2. So you have to take only, let's say higher bound if you take, you have to consider only 4 machines for the KPB. Or lower bound if you take, you will take only 3 machines. So if you run this 512 into 16 code, if you write a code and run these instances, these are the results you will get. And this yellow mark one are the best result you can find in this matrix, right? Like first matrix case, MCT is performing better. Second case, MCT is performing better. Third case also MCT. Fourth case also MCT. Fifth case MCT. Sixth case is KPB. Seventh case, there is a tie between MCT. Yeah, sixth case, there is a tie between MCT as well as KPB. Then seventh case, you can see KPB. Yeah, seventh case also, seventh case there is a tie, not sixth case. Sixth case KPB is better. And eighth case KPB is better. Ninth case KPB is better. 10th case KPB is better. 11th case MCT is better. And 12th case KPB is better. So you can see out of 12 instances, 7 instances MCT is better, including tie cases, right? But if you look into KPB, KPB is resulting better in 6 out of 12 instances, around 50%, right? But other algorithms, they are not performing as good as these two algorithms. Not only there is a 512 cross 16 data set, we have another data set that is called as 1024 into 32. We have another data set called 2048 into 64. Right? Just you double these numbers. 512 into 2, you are getting 1024 into 2, 2048 into 2. If you do, it is 4096, right? Into 128. So these all data sets are available. If you run in a large data set, then only you will come to know which algorithm is performing better, right? I'll tell you a simple illustration before moving to the batch scheduling algorithm. So if you have MATLAB in your system, I have MATLAB in my system. Through MATLAB, you can easily view these files. So suppose I want to write a very simple code, and I'll show you the data sets first. So these are the data sets we have, right? You can see UC high high, UC high low, UC low high, UC low low, UI high high, UI high low, UI low e, UE low low, and US high high, US high low, US low high, US low low. Then you may ask that what is the meaning of this high and low, right? Up to this it is clear, I think. One is uniform distribution, another is type of the matrix, another is high, another is high. So first one represents your task heterogeneity. Task heterogeneity. Second one represents your machine heterogeneity. Okay, like I can say you there is a powerful machines we have. Sometimes we have power of a machine is very less, right? Similarly, a task is a very large task or a small task. So it shows that high task heterogeneity and high machine heterogeneity, whereas second one represent high task heterogeneity with low machine heterogeneity. Okay, so here you can see the values are very, very high. If you see execution time, it is very, very high. High low case, the comparatively to the first one, the value is in the small range. Low high case also it is in the small range, but low case it is very, very small, right? So let us see that how these data sets actually look like. For which, let me open a script. Suppose I want to open a script which is there in my desktop. Okay, let's say there is a demo file, demo.m. Okay, I have opened this file, and let us remove this thing. These are not required. Yeah. So in MATLAB, if you are habituated with MATLAB, then MATLAB is same as our C programming. If you are not habituated also, it's fine. You can understand. So here, when you run this particular file, first we are writing CLC in MATLAB. You can see there is a workspace, there is a current folder, there is a command window, and these windows are used to generate the results and variables and other things. So in order to clear these windows, we are writing CLC clear all and close all. Just we are writing in C programming. If you know, that is called as CLRSCR. That is called as clear screen. We are using in the similar fashion. We are using here. TIC is a measure through which you can calculate the time required to uh, execute the program. TIC and TOC. These are used to capture the time to execute a particular code. And when you run this code, it is going to ask you what is the file name. Okay. So suppose I want to run this code, then let me add to the path, and let me open here the path so that it is easy. Okay, it is asking path. Suppose here it is my dataset file is there. I want to copy this dataset file, and just I need to paste here. Then I want to give u underscore c underscore high high dot txt file as input. Okay. In fact, it is object file, but I have converted it into the text file. Then what it is showing? It is showing the total time lapsed here. It is 38.9 seconds. So once it receives this particular file through fopen, you know also like C programming also we use open command, close command, file open, file close command. So through which through the file name which I given input, that is uc high high.txt with this path, it is going to open that particular file. Okay. Once it is open a particular file, if you open this file here in text format, so here you can see it is showing first one is 512. What 512 indicates? Can anybody guess what is 512? What is 512? So 512 is nothing but the number of tasks, right? and 16 is nothing but the number of machines. So in order to represent in the matrix format, 512 are the number of rows and 16 is the number of columns. And these are the values we have. You can see the values are very large in the case of UC high data set. But if I open the UC high low data set, yes, this is our UC high low data set. If I compare these two data set, you can see the values are little bit low in comparison to this value. In fact, it is very low. It is 4 digit values. It is 6 digit value. Similarly, if I go for UC low data set, there you can see again the values are very low because the machine and task both heterogeneity is low, right? So if you run this one, then it is considering size 1 that is nothing but the number of rows, size 2 is the number of columns, and it read the entire matrix and store in task. Or let me call this is a ETC matrix, right? Expected time to compute matrix. So if I run this code and provide the path, then in the workspace you can see there is a variable etc. If I open that variable, then you can see there is a 512 cross 16 matrix, right? So in this matrix, if you look into this particular matrix closely, you will come to know for all the tasks, which one is better? The column 1 is better, right? Then column 2 is next to the column 1. That means the second best option. This is the third best option, fourth best option. You can see the values, you can understand. 9.1753 e to the power 4. E to the power means 10 to the power 4. This is 2.6312, but 10 to the power 5. It is 2.7511, 10 to the power 5, 2.8022, 10 to the power 5, 3.5261, 10 to the power 5, and so on. And you can see the last machine is in 10 to the power 6. So this matrix is called as a consistent matrix. But because you can see for other tasks also, the similar structure is followed. Right, starting from here, you can see if you go for a fourth task, then it is 4.8803 10 to the power 4, 1.52 into 10 to the power 5, 6.2401 in 10 to the power 5, and so on up to one value that is 1941583. It is in 10 to the power 6, right? Then once you get this value, you can write a simple code that is MET, MCT, OLB, SA, and KPB, and can generate your result, right? So you can use also whatever language you are familiar, like C, C++, Java, Python, or any programming language you are comfortable, you can write the code, right? But MATLAB case, it is very easy. There's a lot of functions are there like Python. So you can use Python or MATLAB to easily write the code instead of going for C and C++. Okay, so this is the summary of the first set of algorithms, which is online algorithms. Now we'll discuss about the offline algorithms. In the offline algorithms, we will discuss about three important algorithms. One is called as mean and mean. Okay, and second one is called as max mean. Third one is called as suffrage. So in the previous case, you have seen there is a particular order we have followed, right? T1 followed by T2 followed by T3 and so on. And you are taking a decision that in which cloud you are actually going to submit that particular task, right? So they are called as your single phase algorithm. But when you go for this offline algorithms or batch scheduling algorithm, we call that as a two-phase algorithm because the scheduling decision is taken in two different phases, not in a single phase. So if you go for mean, is a very popular heuristic. In fact, it is the benchmark heuristic for offline algorithm. Like I mentioned you, MCT, that is minimum completion time, is the benchmark algorithm for online algorithm or immediate mode scheduling, right? So what actually mean actually doing? Here, this heuristic finds the task which has minimum completion time. Okay, our objective is to find minimum completion time. We already know about MCT, right? This heuristic finds the task with minimum completion time and assign the task to the cloud that produces minimum completion time. That means, as I said, instead of one phase algorithm, these algorithms are two phase algorithm. So first phase you are going to apply MCT. Second phase also you are going to apply MCT. Okay. That means it chooses the small task first. If you go for min, it is going to choose the small task among a set of tasks. Okay, like if you have 512 number of tasks, it is going to choose out of these 512 number of tasks, which task is the smallest task. So what is the merit? The main merit is that if the number of long tasks is more than the number of short tasks, assume that in 512 you have observed that there are more long tasks or large tasks in comparison to the short task. Then you can see min heuristic actually providing you optimum make span, or you can say better make span than other algorithm. But if the reverse case happen, if the number of long tasks is less than instead of more than, if it is less than the number of short tasks, in that case you can see min will provide you a poor make span. That is a problem. That's why we are going for second algorithm, that is called as max-min algorithm. But what is the demerit? Yes, as I mentioned, if the number of tasks is more, short task is more, then poor make span it is resulting. Okay? Any algorithm is having a plus and minus like that. Min, although it is a benchmark algorithm, but it is having its some merits as well as some demerit. And average cloud utilization is very less. You know how to calculate average cloud utilization. Once you calculate the make span, then you can consider the local make span and global make span and number of clouds. Through these parameters, what you can do, you can calculate average cloud utilization. So in this case, we are getting very less. But if you go for max-min algorithm, this scheduling algorithm is very similar to min scheduling algorithm. But in min both phases you are applying minimum completion time. Okay, but max or you can say min case you are applying, you are considering the small task first. But max-min case you schedule the long task first. And the merit of max-min is that if the number of long tasks is less than the number of short tasks, then max-min heuristic gives the optimum make span in comparison to the minimum min heuristic. So in this case, you can see average cloud utilization is more than the min heuristic. So it is just like OLV algorithm we have seen. The utilization may be better, but what about make span? Make span is poor. But overall, you have to look into how you can minimize make span. So the demerit of this algorithm is that if long task is more, then it gives a poor make span value. Right? So now let us take a small matrix to understand how actually this min algorithm works. For example, you are given with a ETC matrix, not ECT matrix. This is ETC, generally called as ETC matrix. Okay, you are given with a ETC matrix where you have, let's say, task 1, task 2, like that you have up to m task, and you have, let's say, C1, C2, C3, like that you have Cn minus 1, Cn number of machines or clouds or VMs. So you are given with a matrix. So what you have to do, if you apply min or max-min, as I said, two-phase algorithm, the first phase of min and first phase of max-min both are same. First phase of min and max-min is same. Only in the second phase, min procedure is different, max-min procedure is different. So min and max-min chooses a cloud for each and every task that provides earliest completion time. So once you determine the completion time, and if you put this completion time in a matrix, like this is a matrix, right? We put all the completion time in the matrix. That means this is the completion time if T1 is assigned to C1. This is the completion time if T1 is assigned to C2. This is the completion time if T1 is assigned to Cn minus 1. And this is the completion time if T1 is assigned to cloud number n. Right? So it is after determining this particular matrix, it is finding minimum of each row. Like let's say minimum of the first row is E1 alpha, which is nothing but minimum of I can write E11, comma E12, comma E1n minus 1, okay, dot dot dot, okay, En minus 1 and E1n. So you have to find minimum among these, that is your E1 alpha. Then E2 beta is what? It is nothing but minimum of the second task, E21, E22, like that. It continue up to E2n minus 1 and E2n. Okay, like that, you can see the last one, right? That is nothing but minimum of, you can say em comma 1, em comma 2, dot dot dot. You can say e of mn minus 1 and e of m comma n, right? So you have to find the row minimum. You already seen in Hungarian algorithm, right? You are determining the row minimum. So similarly, in this case, you have to find a row minimum. So if it is a two-dimensional matrix, so it is converted to a one-dimensional matrix here. Right? A 2D matrix is converted to a one-dimensional matrix. Now, once you get this one-dimensional matrix, in the case of min-min, again what you have to do? You have to find minimum of this column. Minimum of the column. But in the maximum case, you will choose maximum of the column. Okay, here you are, after finding this matrix, this 1D matrix, you can find which element is minimum. That is found by min-min algorithm. And the maximum value in the 1D matrix is considered in the maximum algorithm. And their corresponding task and corresponding cloud is selected for execution. Not necessarily the task one is going to execute first. Suppose the minimum is achieved here. Let's say E3 gamma. So its corresponding task is T3. Its corresponding cloud is, let's say, C gamma. Right? So this task will be selected first and it is going to be assigned to C gamma. Okay? It is assigned to C gamma. It is selected first and assigned to C gamma. So next, this task is going to be eliminated and again this matrix is updated. Means completion time is again recomputed. Once you recompute this matrix, again the same process is repeated. Okay, that means you will find the minimum of each row, followed by minimum of each column in the case of min-min, maximum of the column in the case of max-min. Okay, to you can say to select a particular task, right? So let us take a small example so that you can understand that how actually min-min algorithm works. Let me take 4 different tasks, T1, T2, T3, and T4, right? And this is your C1 and this is your C2, right? Suppose T1 is taking 150 unit in C1, 18 unit in C2, 32 unit in C1 and 7 unit in C2 for T2. And for T3 it is 20 and 3. And for T4 it is 50 and 50. Okay. Suppose this data is given to you in the case of min-min. Okay. Many people also work on that, how to determine how many short tasks are there or small task is there, or how many long tasks are there. Many people have also analyzed that, right? And based upon that, they decide whether to go for min-min or to go for max-min. But before that, you should know how actually the min-min algorithm works, right? So what you have to do, this is just like a matrix, right? Let me do rough calculation here. I'm giving this space. So this is just a two-dimensional matrix, right? 150, 18, 32, 7, 20, 3, 50, and 15, right? What I told you, a two-dimensional matrix, you have to convert it to a one-dimensional matrix. You have to find the row minimum. So first row's minimum is, what is the minimum of first row? Minimum of the first row is 18. Minimum of the second row is 7. Minimum of third row is 3. Minimum of fourth row is 15. So a two-dimensional matrix is converted to a one-dimensional matrix. Now, in this one-dimensional matrix, what you will do? You have to find its minimum again. Okay, 2D matrix is converted to a 1D matrix by finding row minimum. Now, you have to find the column minimum after determining one-dimensional. What is the column minimum here? Can anybody tell what is the column minimum? It is 3, right? So, finally 3 is selected. So 2D is converted to 1D, 1D is converted to a scalar element, 1 cross 1. That is called as a scalar element. So where you have 3, 3 is there in this location. That means T3 is selected first. So if you go for the final chart, C1, C2, first you are going to assign T3. To which cloud? To C2. It will take 3 units of time. So in comparison to the previous algorithm, here you can see the order is not T1, T2, T3, T4. First we need to calculate T3, then we'll look into other tasks. Right? There is no predefined order. So that you can only do if you have knowledge about all the tasks. That's why this algorithm is called the offline algorithm or batch algorithm. So once T3 is done, you can remove T3 from this particular list. Now, what about ready time? You may ask the previous cases. I told you about ready time. What is the ready time here? Initially, the ready time is 0. But now, the ready time is 3 for C2. Because one particular task is assigned to C2. Okay. As 3 unit is taken in C2, I have to add plus 3 in each and every task. Each and every task execution completion time in C2. Right? I'm adding 3 in each and every task, but have to be in C2, not in C1, because C1 is empty now. Okay, that is the first step. Is it clear? Is it clear? Because first step, if it is clear, then only you can understand the entire process. Is it clear? Okay. So now what we will do? Now first round is over. We'll go for the second round. Second round, what we have? We have 150 and 18 plus 3, right? So you can say this is 150, 18 plus 3 is 21. Second task, it is 32 and 7 plus 3 is 10. Third task, it is 50 plus 15 plus 3 is 18. Right? So it is the two-dimensional matrix. So what you have to do in order to convert it to a one-dimensional matrix, you have to find the row minimum. So row minimum is, you can say in this case, row minimum is 21, row minimum is 10, row minimum is 18. Okay. And column minimum, if you find, this is a one-dimensional matrix. Now, if you find column minimum, so out of these 3, the column minimum is 10. 10 means where you are getting 10? 10 you are getting here. That means T2 is assigned to C2 for 7 unit of time, and its completion time is 7 plus 3, that is 10. Its execution time is not 10. Execution time is fixed already, right? It is already estimated, right? Only because of 3 unit of time is taken by T3, so it will be complete by 10. Okay, it will be complete by 10, right? So you can see C2, it is we are adding 7. So total time C2 is busy, it is 10 unit of time, but C1 is completely free till now. Now what you have to do? Now T2 is successfully assigned. So T2 is going to be removed from this queue. And as 7 unit of time is added because of what? Because of T2, I am going to add 7 unit here. So this red color indicates your ready time. And this green color represents the execution time, right? So it says that 18, for example, T1 case, what it says? It says that 18 is the execution time, but ready time is 10. Why ready time is 10? 3 unit you have given to T3, 7 unit you have given to T2. So total time is 18 plus 3 plus 7. That means it is 28, right? In that manner, we are calculating. Okay, now what I'll do, I'll again go for the another round. Okay, so I'm taking only T1, T4 is left. T1 is 150 here, and in C2 it is 18 plus 3 plus 7, so it is 28. And T4 case it is 50, and in C2 it is 15 plus 3 plus 7, it is 25. So it is a two-dimensional matrix. If you convert it to a one-dimensional matrix, so you will get 28 and 25, right? And if you convert one-dimensional matrix as color element by finding their column minimum, so you will get 25. Where you have 25? Here you have 25. That means the next task which is going to assign, that is T4. It is how much time it will take? Can anybody tell? How much time T4 will take in C2? How much time it will take T4 in C2? It is 15 unit of time. It is 15 unit of time. But its completion time is 15 plus 7 plus 3, that is 25. Right? So now T4 has successfully completed its assigned into C2. Now you are left with only T1. So if you go for the last round, T1 is nothing but it is 150 in C1. Yes, you need to add ready time. Ready time is now increased to another 15 because of T4. 3 is because of T3. 7 is because of T2. 15 is because of T4. So 150 plus here it is 18, 28, 38, 5. So it is 43. 15, 15, you check once, 25 plus 18. Yes, 43, right? It is again a 1D matrix. If you find row minimum, then you will get 43. Again, column minimum, it's 43 only. So it is also going to assign to C2. So finally, T1 is assigned to C2. It is going to take 18 unit of time, but its completion time is 18, 3, 7, and 15. You have to add all. So if you add all, it is coming 43. And here it is coming 0. So if you calculate the make a span using mean, it is 43. Okay. But if you calculate utilization is nothing but 0 plus 43 divided 2 into 43. How much you will get? You will get 43 divided by 86. That means 0.5. Or you can say 50%. Equal to 50% you can write. Right? Only utilization is 50%. That's why I told you in min case, the utilization, if you calculate, this is not utilization, this is average utilization, right? Average utilization is more in the case of max-min algorithm, but in the case of min algorithm, average cloud utilization is very less. Right? That is the drawbacks of min algorithm. Okay. So this is the detailed calculation is given in the slide. Okay. Now I'll tell you about the next algorithm, that is max-min algorithm. Right? Okay. Let us go for the next algorithm, max-min, using the same input, so that we can compare the performance of max-min and min. So if I consider T1, T2, T3, and T4, and C1 and C2, so 150, okay, just a minute. Yeah, let us write like here so that we can write the ready time 150 and 18, 32, 7, 20, 3, 50 and 15. Right? So these are the two different cloud C1, C2 and four different tasks and their expected time. So this is a, you can say ETC matrix. Okay, so here I'll do the raw works and here I'll show you the Gantt chart, right? So what actually maxmin is doing? It is finding the row minimum like maxmin. So if you find take this matrix 150, 18, 32, 7, 20, 3, 50 and 15. The row minimum is you can get 18, 7, 3 and 15. Okay, which is a one-dimensional matrix. Again, this you have to find after finding row minimum, you have to find the column minimum. So column minimum is 3, which is color element. Okay. In the case of min you are doing this process. This process is for min, not for max min. You are finding row minimum followed by column minimum. But what actually we are doing here in the case of max min, you will take the first step as it is. First step you take as it is. Like this is your two-dimensional matrix converting 2D to 1D. That is 18, 7, 3 and 15. It is as it is. But instead of choosing the minimum value here, what you have to choose? You have to choose maximum value. Maximum value is 18. So this is the process of maximum. So first I need to choose this particular task, that is 18. So if you go for the Gantt chart, C1, C2, first T1 is assigned to C2, that is 18 unit of time, right? And once T1 is successfully assigned, this 18 is the ready time, right? That I need to add with other tasks, those who are going to be assigned to C2, right? Now, if you calculate the ready time is again, if you calculate the ready time, it is 18. Okay, completion time is 7 plus 18 in this case, right? So, okay, after assigning T1, if you calculate, after calculating ready time also, if you choose another task, you want to choose T2, one task from T2, T3, T4, then you can see the matrix is looks like this one, 32, 18 plus 7 is 25, this is 20, this is 21, this is 50, and this is 15 plus 18, it is 33. So it is a 2D matrix, right? So if you convert it to a one-dimensional matrix, then minimum of these two, this row is 25, minimum of this row is 20, minimum of this row is 33. But we have to choose the maximum one. Maximum one is your 33. 33 means this particular value. So the next one we are going to assign, that is called as T4. So T4 is assigned. T4 is assigned next. And is assigned at 15 unit here. So 15 plus 18. So it is going to complete by 33 unit of time. Right? Now what I'll do, once T4 is assigned, I'm going to remove it from task queue, you can say. And I will add 15 unit of time in other task. Okay. Now again, if you reevaluate the same calculation, so it is 32 here, 42. Here it is 7 plus 8, 18. That is, you can say 25 plus 15. That is 40. And here it is 20. 18 plus 3 is 21 plus 15. That is 36. So it is a 2D matrix. Now, if you convert it to a 1D matrix, you have to find a row minimum followed by the here also row minimum, then followed by row maximum, column maximum. Column maximum, it is coming as 36. 36 is nothing but this particular value, right? So the next task that is going to be assigned, okay, the next task that is going to be assigned is T3. But we have to calculate their minimum completion time. So if you look into T3, Okay, T3 case, T3 is taking 20 unit of time in C1 and 36 unit of time in the C2. So you have to choose C1, not C2. You have to choose. Uh, you have to choose C1 for T3 because the completion time, if you calculate, as I said, both cases we are calculating completion time, right? So if you assign here, it is going to complete it 36 unit of time. So this selection is actually done for choosing the task, not this is for the completion time. Okay, you may get earliest completion time also, like here I am getting 20. So T3 is now assigned to C1. Okay, if you assign here, then what is the time? The time is 36, which is not good. So you have to find minimum completion time. So minimum completion time it is 20. That's why we have assigned to C1. Right? So now what I'll do, I'll remove T3 from the queue and I will add 20 to C1. Whatever task is left out in their uh, C1 value, you have to add 20. Right? That's a 32 plus 20 is now the completion time of T2. So if you go this one, then you will get 52 here. Okay, here you will get I think 40, right? Row minimum you will get 40. There is a single element, so column minimum is 40. So what I'll do, if I assign it to the first one or the T4, if you look into T2, if I assign here, then it is taking 52 unit of time. 20 plus 32, that is 52. But if I assign in C2, that is 7 unit of time, 18 and 15 because of T1 and T4, right? So it will complete its execution at what point of time? 40, right? And C1 is busy for 20 unit of time. So if you calculate max span is 40, that is the overall maximum. And if you calculate average cloud utilization, it is 20 plus 40 divided by 2 into 40. So it is 60 by 80. How much you will get? 60 by 80 is 3 by 4. That is 75%. Okay. Or you can say it is 0.75. Okay. So in comparison to max mean is actually providing better resource utilization. Okay, average cloud utilization is improved in comparison to mean. That is the advantages of using mean. Max mean over the min. If the but based upon the has to determine how many long tasks there are, short tasks there, then only you can decide whether to go for min or max min. But luckily in this case, in the make a spend case also, you are getting good result because if you go for min, like if you go for min, if you compare min with max min case you got make a spend is 43. In this case, you are getting 40. Average utilization, average cloud utilization, or you can write average utilization. How much you are getting? There you are getting 50%. Here you are getting 75%. So in the both parameters, you are getting good result in the case of max spend, right? But when you run a large data set, you will see most of the cases min is performing better. Okay, so this is the chart you can see which we have seen. If you draw the Gantt chart, it will be look like this one. As min choose the small task. So what happened? There is a large task is coming here. If you assign it to R1, it takes more time. That's why min suffers here with poor make aspect or its utilization is low. But what happened in this case, in the maximum case, it took the large task first. It has settled the last task first. Then it thinks about the small task. That's why their make SQL is better than the min algorithm. Right? So can you try with another example? Right? For example, if I give you another example, suppose there is a task T0. Let us start from T0, T1, T2, T3. And let's say this is M0, M1, machine 1, machine 0, machine 1. And let's say 2, 4, 3, 6, 4, 10, 30, and 70. Can you try with min and max min and tell me what is your make span? I'm giving you 5 minutes time. Calculate using min and max min and tell me how much time, what is the make span value in min and make span value in the max min. Okay. So let me show you. But if you are trying, I'll give you some time. Otherwise, I'll tell you in the process. You can check that whether your result is matching with my result or not. So min case, what we are doing? Let's say I will choose the minimum one. Okay. So let us take the matrix like this: 2, 4, 3, 6, 4, 10, 30, 70. So the minimum one is 2 here. Minimum one is 3 here. Minimum one is 4 here. Minimum one is 30 here. Out of which the minimum is 2. So the first task is assigned is T0 to the machine 0. Right? It is taking 2 units of time. Once the first task is done, it is removed, then you have to add +2 in other task. Okay. Then you calculate again. If you calculate again, you will get 3 plus 2 and 6. It is 3 plus 2, it is 5, 6. 4 plus 2 is 6, 10. Here 32 and 70. So the minimum one you are getting here, it is 5. Here it is 6. Here it is 32. So again, 5 is the overall minimum, right? So then you can assign T1, okay, T1 to the first one only, because it is taking 3 units of time. So total it is 5, and it is removed. Then I have to add +3. Okay, I have to add +3 to the machine 0. Okay, so next, if you calculate the minimum one, you will get 4 plus 5, it is 9 here, it is 10 here. Here is 32, 35, and 70. So the minimum one, it is 9 here, minimum one is 35, overall minimum is 9. So I'm assigning T2 here with unit is 4. So total is 4 plus 3 plus 2, you will get 9, right? Now it is removed from the queue and the last one is left. So you have to add +4, right? So still T3 is going to be assigned to M0 only, right? So it is taking 30 unit of time. So overall completion time, if you see in the case of machine 0, it is 34, that is in 39, right? But whatever M1, there is no task is assigned. So if you calculate make span, it is 39. As other is other machine is 0, so you can say average utilization is 50% or 0.5. Okay. Now if you go for max mean, if you look into max mean for the same problem, okay, so what you will do here, you will take 2, 4, 3, 6, 4, 10, 30, and 70. Okay, 70. The minimum you will choose is 2, minimum is 3, minimum is 4, minimum is 30, but you have to choose the maximum one. That means T3 case you have to assign to M0 first. Okay, so it is going to take 30 unit of time. Right, it is going to take 30 unit of time. Once it is completed, okay, once it is completed, let me write here again so that I will show you the step by step increase of ready time. So it is 2, 4, 3, 6, 4, 10, 30, and 70. Okay, so T3 is successfully assigned. So 30 need to be added into, you can say, other task, right? Now, what you have to do, you have to find the matrix is now 32, 4, 33, 6, 34, and 10. Minimum is here 4, minimum is here 6, minimum here is 10. So maximum one you will choose, that is your T2. So T2 is assigned to minimum completion time. If you look also, here you will get 10 only, right? 10 in the second machine, right? So it is successfully executed. Now plus 10 is going to be added to T0 and as well as T1, right? Now if you look into the next one, so you will get here 32, here 14, here 33, it is 16, right? Then the minimum one you can find here, it is 14, minimum one you can find here, it is 16, maximum is 16. Maximum value we are getting is 16. Okay, so that task need to be assigned first. So that is the task number, you can say T1. So I can write T1 is assigned to M1. So it is taking 6 unit of time. Okay, so now task 1 is removed. So I will add plus 6 here. If you take the matrix is says that is 32 here. It is 20 here. 32 and 20, out of which the minimum one is 20. Okay, and maximum one if you find also there is one element, that's why it is 20 only. So T1 T0 is assigned to 4. Okay, so the total completion time we are getting here 30. Here you are getting total completion time is 20. Okay, so in this case, in maxmin case, there is another case where maxmin is performing better. Maxmin is 30, sorry, not 20, 30. And if you calculate average utilization, the average utilization is, you can say 20 plus 30, 2 into 30. So you will get 50 divided by 60. Okay, 5 by 6. How much you will get 5 by 6? It is around 84% or 83.34%, you can say. Okay. In this way, actually, the min and max min works. But in this case also, you can see both case, in max min case and average utilization case, both case if you compare, then max min is better than the min. But if you learn with large data set, you will find min is better than the max min algorithm. Right? Now we'll go for another algorithm. That is the last algorithm here. That is called Sufferage algorithm. It is also a very popular algorithm, which which provides a better result in comparison to min and max min algorithm. Okay, let us discuss about this algorithm. So Sufferage heuristic is based on the idea that better mappings can be generated by assigning a cloud to a task that would suffer most in terms of expected completion time if that particular cloud is not assigned to it. What is the meaning of this statement? It says that, for example, a person has two offer. This is, let's say, offer 1. This is your offer 2. And let's say offer 1 is the best offer for that particular person. Just you can imagine about the campus placement. First best offer is, let's say, it is 50 lakhs, right? And there is another offer for that particular person, and that is 48 lakh, right? Two offers. The person can choose one of the offer based upon the reputation of the company, based upon the salary package and other things. So the best offer is 50 lakh in terms of price, in terms of rupees, if you see, it is 50 lakhs, right? So, but this offer is, let's say, withdrawn due to some issue. Okay, assume that. Then the student has to go for the second offer, right? So how much the student can suffer with respect to price? That is 2 lakh, right? That is considered as a suffrage amount, or you can say suffrage value. So here it says that whenever you are mapping your task with the cloud, you have to look into expected completion time that we are looking. And if a particular cloud is not assigned to that particular task, then the task need to be assigned to any of the cloud. It may be the best cloud, it may be the second best cloud. So we need to calculate what is the suffered value. And the person is having more suffered value that need to be addressed first. For example, for another person case, first is, let's say, first package is, let's say, 40 lakhs, second package is 20 lakhs. So if he is not getting this offer, then the sufferer's value, if you calculate, that is nothing but 40 minus 20, that is 20 lakhs. So in comparison to this particular student, this student has to suffer more, right? 20 lakh is, it is more. So based upon that, we will perform the ordering of the task. For example, here you can see, this is a non-technical example. Let us see in our context. Let the sufferer's value of a task Ti, that is a task Ti, is the difference between its second earliest completion cloud. Second earliest completion cloud is My. Okay. And its earliest completion cloud is Mx. Okay. Suppose Ti is taking 40 unit here and 48 unit here. So this is called as your earliest completion time. This is called as your second earliest completion time. Okay. So that is, using Mx will result in best completion time for Ti, and using Mx the second best. So if the first option is not given to that particular task, the task has to be suffer for 8 unit of time. It is assigned to My instead of Mx. Right? So now let us see that for this example how it actually works. Here you are given with 4 different tasks, right? And you are given with 4 different clouds. Now you tell me, for T0 which cloud is best? For T0 which cloud is best? C0? C0, right? Which cloud is second best? The second best is C1. So if it is not assigned to C0, if T0 is not assigned to C0, so it will be assigned to C1. If not C1, C3. If not C3, then C2. Right or not? So if it is not assigned to CU0, which is its earliest, you can say, completion time, then it should be assigned to second earliest completion time, that is C1. So the sufferage value is nothing but the difference between the time it takes in C1 and the time it takes in C0. So it is 48 minus 40, you will get 8. For T1, the best cloud is 50, and the second best cloud is 82. So the Sufferage value is 82 minus 50, that is 32. T3 case, 55 is the best, 68 is the second best. So 68 minus 55 is 13. T3 case, let's say 52 is the best, 60 is the second best. So 60 minus 52, it is 8. Now you have Sufferage value of each and every task. Can you tell me which task is suffering more in this case? Which task is suffering more? T1, right? Because T1 value is 32. That's why T1 needs to be assigned first. To which cloud? Based upon the completion time. Completion time case, if you look into T1's best cloud is C0. So first T1 is going to be assigned to C0, right? Now what we will do? Now your task T1 is removed from the task queue. It is not there. So as it is taking 50 unit of time, T1 is taking in C0, you have to add 50 here. Add 50 here. Add 50 here. Now you calculate the Sufferage value. So if you calculate Sufferage value, for the T0, best cloud is now C1. Second best is C3. So 50 minus 48, it is 2. Right? For T2 case, it is 93 minus 68. So it is 25. For T3 case, it is 78 minus 60. That is 18. So out of these values, who has suffered most? T2 has suffered most. So T2 need to be assigned based upon its completion time. Which one is the best cloud for T2? If you calculate minimum completion time, you will get, I think 68 is the best in the cloud number C1. Right? Now what I'll do, T2 is going to be removed from the queue. Remove T2 from the queue. Okay. Now 68 need to be added here. As well as 68 need to be added here. Right? Now you calculate the Sufferage value. Sufferage value, if you calculate here, 50 plus 90 is 40 and it is more than 100. So I'm not considering 90 and 50. So 90 minus 50. Earliest time and second earliest time you have to calculate. 90 and 50 you will get 40. Right? But in this case, in the second last case, if you look into, so it is taking 78 unit time here, and the second is I think 102. Okay, if I'm correct, it is 102. It is 128. It is more. 108 is also more. So it is nothing but 102 minus 78. Okay, how much it is? 24. Out of which maximum Sufferage value is held by T0. That's why T0 need to be assigned first based upon its minimum completion time. The minimum completion time for T0, it is 50 in the cloud number 3. Right? Similarly, if you go for, okay, after that you can remove T0 from the task queue. You are left with T3. And before that, you have to add plus 50 here. Okay. And a T3 case now, if you calculate Sufferage value for T3, okay, it is nothing but 78 is the best machine. Then 50 plus 52, 102 is the second best machine. So its Sufferage value remains same. 102 minus 78, it is 24. So T1, T3 need to be assigned first. Next, and it is going to take 78 unit in C2. So now we have completed the task allocation. So it is taking 50 unit in C0, 68 in C1, 78 in C2, and 50 in the C3. Okay. So if I remove it, you can see For T0, you have selected. Okay, sorry, this is 40, not 50. This is 40, right? This is 40. T2 case. Oh, sorry, just a minute. First is T1, right? T1 is 50. T1 is 50. Then T2 is 68. T0 is 50. And T3 is 78. Okay. So now, if I ask you what is the make span? Make span is 78. And if I ask you calculate the average cloud utilization, then it is how much? Average cloud utilization is 50 plus 68 plus 78 plus 50 divided by 4 into 78. Okay, so if you calculate 50 plus 68 plus 78 plus 50, they will give 246. Then 4 into 78 will give 312. 246 divided by 312, it is 0.7884, that is 78%. Right? The make span is 78. If you assign, you can say T1 to M0, T2 to T2 to C1, T1 to C0, T2 to C1, then T0 to C3, and T3 to C2. Okay. But if you go for make span using, you can say min algorithm, then only you can compare. In this slide, you can see the comparison is given in between the sufferage as well as min. So if I take the same value and calculate min, 40, C0, C1, C2, C3, T0, T1, T2, T3, 48, 134, 50, 50, 82, 88, 89, 55, 68, 94, 93, 52, 60, 78, 108. Okay. So in this case, if you find the row minimum is coming as 40. Again, row minimum, if you calculate, you will get 50. Row minimum is 55. Row minimum is 52. Out of which the minimum is 40. That means T0 need to be assigned first. And T0 need to be assigned to M0, right? Which is taking 40 unit of time. So T0 is now going to be removed here, right? Let me remove T0, right? And what I'll do, I'll add here plus 40, plus 40, plus 40, plus 40. Now minimum if I found, it is 82 here. Minimum if I found, it is 68 here. Minimum if I found, it is 60 here, right? Out of which the minimum one is 60, right? So T3 is assigned to which one? 60, that is C1. Okay. T3 is assigned here, that is C1, that is 60. Right? Then what I have to do? I have to remove T3 from the queue. Let me remove T3 from the queue. And I will add 60 here as well as here. Okay. Now if you calculate row minimum, it is 88 is the minimum here. Here the minimum, I think you will get is 93. Okay. Out of which the minimum one is 88. Then T1 need to be assigned. Where we can assign T1? You can assign here as 88. Right? T1 is assigned to C2. Then T1 is removed from the queue. It has removed, sorry, I have removed T2. T1 I have to remove. Okay. So now I have to add 88 here. Now the minimum one I think you are getting is 93. So T2 is assigned to the last one, that is 93. So 40, 60, 88, 93. So what is the make span you are getting here? The make span you are getting here, it is 93. And if you calculate average cloud utilization, it is 40 plus 60 plus 88 plus 93 divided by 4 into 88. Okay, how much you will get here? 40 plus 60 plus 88 plus 93, you will get 281 divided by 4 into 88, that is 352. So 281 divided by 352, you will get 0.79829. That means it is around, you can say 80%. But what is the make span in the previous case? It is only 78. You can see also here, because of T2, T2 is the min case, who is taking more time? You can see T2. So it is 93. Right? But in the case of suffrage, who is the tallest one, you can say, the longest one? T3. Okay. So T3, that is 78. So obviously, for this particular example, we can conclude that suffrage is performing better in comparison to min, because it is calculating. If you are not getting the best offer, if you go for the second best offer, or in this case, minimum completion time or second minimum completion time, then how much we are suffering. And the task which is suffering the most, it is assigned first. So that's why we are getting advantages in the case of suffrage. Okay. In comparison to min also, it is performing better. Now you may ask me that if I take a large data set, whether min outperforms suffrage or suffrage outperforms min, that you can see in this slide. Like if you run the same data set, which I told you 512 cross 16 data set, and if you compare these algorithm min, max min, and suffrage in 12 different instances, right? So you can see for the first 4 instances, we are getting good result for min. Fifth instance, we are getting better result in suffrage. Sixth instance also suffrage. Seventh instance min. Eighth instance suffrage. Ninth instance min. 10th instance suffrage. 11th instance min. And 12th instance suffrage. So you can see 7 out of 12. 7 out of 12 instances min performs better. That's why it is called as a benchmark algorithm. But what about suffrage? Suffrage outperform only 5 out of 12. Okay. But there are, you can say, most of the cases as min is better. That's why it is considered as a benchmark algorithm. And if you can execute the 512 different tasks and you can get a better make span than this one, then that is also a better one, right? If you can run a particular algorithm where your result is less than this one, then obviously that is considered as a best algorithm for min. Okay. So this is all about the task scheduling in cloud computing. And now, okay, you give me 2-3 minutes time. I'll tell you something related to another topic.
I think they are not right now.
What happened?
No, nothing, sir. Nothing to ask right now, sir.
Okay, okay. Just one. I'll take another 20 minutes only. Just I'll introduce a topic so that you will come to know what are the current work going on. Like, you can say in the field of cloud computing. Yeah, there is another research area where people are working. Uh, in fact, this slide is prepared by my guide, Professor Prasanjana. So I am using his slide. So the main limitation of if you go for the traditional cloud computing, already I mentioned some of the limitation. Like I told you, one connectivity, internet connectivity is one of the major issue. Security is one of the major issue. Legislation is one of the major issues. Apart from that, there is a main limitation of traditional computing, cloud computing is that we have end-to-end delay. Like if you consider the IoT based architecture, Internet of Things based architecture, you can see there are three-layer architecture. One is IoT, and another in the top layer we have cloud. So IoT or any devices you can say. So like you can see our desktop and laptop, these are also called as devices. So what we are doing, we are storing the data in the Google Drive, right? Or you are using a particular applications. So while you are storing your data or doing some kind of computation, your data is sent to the cloud or it is synced to the cloud. Okay. And suppose you are using a new device, you want to download a particular file, you can download it from your cloud to your local device. So the main problem what we are getting here, that is called as end-to-end delay, because the distance between the cloud and the end devices causes the latency issues. In fact, we can say the cloud is very far away from IoT devices. That's why the communication time is more. So this actually creates a problem if it is a time sensitive application, or you can say real time applications, such as you can say disaster management, airline system, and those applications where minor delay can cause a big problem, right? Or you can say healthcare also. If there is a abnormal reading by a particular patient, then immediately it need to be notified to the doctor, so the doctor can take actions to save that particular patient, right? So such application, minor delay can cause a big problem. In such cases, pushing the data to the cloud or retrieving the cloud is not a good solution. And due to the increase in the increase of the load in the cloud, or many organizations are moving to the cloud, so we have very large number of applications, so we have traffic congestions as well. Like in a particular area, if more people are using mobile services or internet services, then internet services are going to be slower. Moreover, if you look into energy consumption perspective also, it increases carbon footprint in the atmosphere, right? So as the carbon footprint is happen, that is also harmful to our environment. Also indirectly, it is harmful to us also. So in order to avoid that, what we have a new terminology that is called as fog computing. And moreover, if you look into these devices are having a limited processing power, limited memory, and limited battery power. So these are the drawbacks of this one. That's why we are moving to the cloud. So due to this particular constraint, so that also causes the issues that everything you need to push to the cloud. So that is not a good solution because it is very far away from the cloud. Now, if you look into this situation, there is a new terminology introduced by Cisco, which is called as fog computing. So in fog case, it is an intermediate layer between the IoT devices and cloud. This is your IoT devices and this is your cloud. Earlier, what happened? All the data we are pushing to the cloud, and we are getting the results from the cloud as well. But now we have an intermediate layer that is called as fog layer, where we have fog devices, so that whenever IoT devices need some kind of computation, bandwidth, or you can say memory, or in terms of energy consumption also, it is very less to get the services from the fog nodes rather than referring to the cloud. So if you calculate the latency without considering this fog layer, so if a device is sending something into the cloud, so that is nothing but the transmission from device to the cloud. This represents this particular arrow. And once the data is reached to the cloud, cloud is doing the data analysis or processing of the data. That also takes some amount of time. And once the data is processed in the cloud, it will be again returned to the cloud to the IoT devices, which also takes time, which we call as transmission time between the cloud and devices. Now, as we need a middle layer, so fog is introduced in that particular purpose. So what happens here? First, the IoT devices need to communicate with the fog nodes. Fog node can do the data analysis. Fog node can do some kind of processing. If the processing is done by the fog node, the result is going to be returned to the IoT devices. So what we can say, the communication time, or you can say latency, is drastically reduced if it is solved in the fog nodes. But if fog node is not capable to execute that particular task and not capable to process some information or execute some information, then the fog in turn dispatch it to the cloud, and cloud has to do the data analysis, and it will return the result to either fog nodes or it can return the result to the IoT devices, the way we are doing in the traditional cloud computing system. That is the main reason why we need fog computing. This is one of the architecture you can see. Like we have nowadays, we are having a lot of sensors, right? Our mobile phones are also associated with various type of sensors. Like we have fingerprint sensor, uh, we have face recognition sensor, or smart watches are having also different kind of sensors. It is, we are able to know the number of steps, we are able to know the BPM, we also know about the SpO2, we know about the blood pressure and other things, right? Or the stress level. So these all are the nothing but the IoT devices, right? So number of devices, if you see in the bottom layer, it is in terms of billions. But if you look into the cloud, the number of servers we have or number of data centers we have, that is in the thousands. So billion of devices are dependent on the thousands of the data centers or the devices, you can say. But the problem is that as there is a huge gap between cloud and edge devices, the delay is significantly increased. That's why we want the same service which is provided in by the cloud, or you can say uh, some of the services, if we need to, if it is available with the fog nodes, then the delay can be minimized. So in the IoT environment, we require both cloud and fog. First, we will check with the fog. If it is fulfilling the requirement, that is fine. Otherwise, we will send to the cloud. So fog is actually the intermediate processing or tangent storage, you can say. If it is capable to do it, your problem is solved. If it is not solved, then in fact it is going to the cloud, the way we are going in the previous computing paradigm, that is cloud computing. So sensor data is processed in the fog before it is sent to the cloud. So if you look into the idea of the fog computing is that it is what it wants to make the resources available near to the IoT devices, right? So it extends the cloud near to the IoT devices. That's why fog is simply called as from core to edge computing. So based upon the letter of F and O and G, this is called as fog computing. The full form is called as from core to edge computing. And fog is in fact closer to the cloud. If you see our environment, in our environment, fog is close to ground rather than the cloud. That's why fog is a very popular paradigm, but it cannot substitute the power of cloud. cloud is very contains so many servers, so many data centers, right? But that much power we cannot provide in the fog layer. But some tangent storage, you can say, or some intermediate level of processing that we can provide in the fog layer, right? That's why fog is actually not a substitute the cloud, but it is an complementary. So to solve the problems faced by cloud computing, that is the main problem is that the end-to-end delay that can be uh, avoided by the help of the fog devices. So fog computing is a highly virtualized platform that provides you computing, storage, networking, just like cloud, but it is not in the massive in power. Okay, and between the end user and data center of the traditional cloud computing. Like here also you can see like these end user devices like our mobile phones, you can say laptop, desktop, smartwatch, or you can say in hospital we are having different kind of sensors to measure SpO, to measure our heart rate. So these are connected to the fog nodes. Like here you can see there is a fog nodes here, there is a set of fog nodes here. They may be also connected through local area network or router, switch. These are also can considered as a fog devices. So they can provide immediate results. And if it is not capable and through wide area network, it is connected to the cloud server. And if you want to compare the traditional cloud computing with fog computing, moreover, if you look into the cloud scenario, it is a centralized system because we are not connecting to multiple data center at the same time. So our services are actually generally provided from one data center, right? So in that context, it is saying the computing model used in the case of traditional cloud computing, it is a centralized model. But if you go for fog computing, it is completely a distributed model where fog nodes can be deployed in a distributed manner or it can be put in the centralized manner. And if you look into the cost, cloud cost is obviously very high because it is in massive in power. But for case, the cost is low because it is providing you ad hoc deployment, temporary deployment. And with or without planning, you can deploy these fog nodes. But you know, in order to deploy a cloud data center or servers, what you need a proper planning. If you look into resource optimization perspective, the resource optimization in the cloud is a global one, but for computing case, as it is available in your local area network, so it is a local optimization. And if you consider the size, cloud case it is very large in size, but fog case the size is very small. We have very less number of fog nodes or small capacity of the fog nodes, you can say. But a large number of small fog nodes from a large number of fog systems. It depends upon the differences, but in comparison to cloud, it is less in actually size. And if you look into mobility, and last class also I told you about that is SG Ice Cube. So in which we have a containers, right? 40 feet containers, and these containers are actually having our servers, right? So in that case, the movement is easy. But if you look into our data center, the data centers are having no mobility power. They don't have any mobility. So mobility management in the case of traditional cloud computing, it is uh, low, or you can say mobile. There is no mobility also. But for case, it is movement is a little bit flexible in comparison to uh, cloud, right? But if you go for the vehicular cloud computing, like you can say, considering the movement of the movement using a 40-feet container, in that case, the mobility management is easy in the case of cloud computing. But it is hard in the case of fog computing. And latency is very high in the case of cloud computing. But fog computing case, the latency is very low. Similarly, reliability wise, cloud is more reliable than the fog. And if you are dealing with the cyber domain applications, so it is suggested to go for traditional cloud computing. But if you want to do cyber domain application or cyber physical applications or time critical applications. Any application which leads to time sensitive or real time applications. So uh, fog will provide an important framework to do that one. There are some characteristics of the fog nodes. The storage is transit, right? Computing process facility, if you see, to process the data before it sends to the cloud, it takes a quick decision whether it can execute it or the data need to be transferred to the cloud. Similarly, in terms of network connectivity, you can see to connect end devices with the fog nodes. Its range is only to connect with the fog nodes or transfer the data to the cloud, just like an intermediate layer. And some of the examples of the fog devices is servers, routers, switches, and access points. There are different types of data handled by fog devices. Like we have very time sensitive data and less time sensitive data and not time sensitive data. Means whole application and data can be categorized into three parts. If it is very time sensitive means once you know something, you have to immediately react, right? Immediately take some actions. So data which is, should be analyzed within a fraction of second is called as time sensitive data. Like surveillance using camera. You know, many places we are putting camera. In camera, you have identified something. Okay, like somebody is stealing, somebody is taking something from some important thing from a particular place. So you have to immediately take action in that. So such type of applications are very time sensitive. Or you see our aeroplane system, we are getting signals, right? And you can see immediately if there is some issue or if there is another aircraft nearby, we have to immediately respond, right? So such are very time sensitive applications. Next is less time sensitive data, where the data which should be analyzed after seconds and minutes. If there is a delay in some seconds or delay in some minutes, so it is not going to create any problem. So that is called as non-critical healthcare data. Right? If there is some data where you have a time constraint, right? Then you can go for the consider that as a very time sensitive data. But if there is no, you can say time constraint, you can consider that as a less sensitive time sensitive data, right? And there is not time sensitive data, like some data you can wait after hours or weeks and days, then you can go for it is not at all a time sensitive data. Like healthcare data, which is not related to the death of a patient, can be considered as not time sensitive data, right? Some of the features of fog you can see, that is low latency and location awareness. The delay is very less, and based upon the location, you can put the fog nodes. That's why it is called as ad hoc deployment. It also supports a geographical distribution. It is not limited to one location. It can be distributed in various places. And end device mobility, right? It is one of the features because you know some of the IoT devices having mobility power, so they can connect to different fog nodes present in different places. So capacity of processing high number of nodes. Okay, it is not that much capable as cloud, but you can process something, so some nodes using the fog devices. Wireless access, it is also providing you real-time application and heterogeneity. And if you are interested to do some research work in the fog computing, this is the complete fog computing system flow diagram. You can work in the architecture level or you can go for the algorithm level. Okay. There is a popular problem. People are working in the field of fog computing that is called as offloading. That we are offloading some of the tasks to, uh, you can say, we offload some of the tasks to fog devices. Upload is just like similar to the uploading mechanism. If you cannot handle it, you can simply give to the fog nodes. Fog node can provide you an environment to execute it, right? There is another popular simulator. Just I'll tell you brief about that thing. Then we'll conclude. There is a tool called as iFog Sim. So I will tell you a brief about that one. Yeah, you can see here. There is a tool called as iFoxing, which is developed by a group of researchers from University of Melbourne as well as from Indian Institute of Technology, Kharagpur. So this paper you can go through. It is a very nice paper published in the year of 2016. It talks about one tool that is called as iFoxing. Like all of you know about cloud analyst, right? We have discussed about cloud analyst and cloud sim. So this particular tool, if you that is also publicly available, and this is the architecture of this particular tool. If you want to design some kind of a topology, also you can use this iFoxim tool. For example, I can give you a simple demo. I'll also share. Let me show you a small demo. Let me put it in my local drive. Okay, this is your iFoxy master. You have to download. I'll share this file with you, and you will get the zip file, and you try to extract that zip file. Okay, then you need some configurations like you need Eclipse. Like in the case of cloud analyst, I told you to go for NetBeans, right? But in this case, you can use Eclipse, but you can use any IDE. There is no restriction on the IDE. But they suggested you should use the Eclipse framework, right? And you can see, uh, yeah. First, you need to install Eclipse and download this iFog sim master zip file. Okay, and you have to extract it. Then you can open Eclipse. Let me see in my computer Eclipse is there or not. Yeah, Eclipse is there. You can open it. Once you open Eclipse, then you have to create a Java project. Okay, let us launch it. Yeah, now it is open. Okay, so suppose you want to create a new project. Let me delete the old project so that I can show you. Yes, you have to create a Java project with any name. For example, I want to create a Java project with name of NIT Warangal. Then, okay, I have created it. Then you have to provide the path after creating the Java project with name. Yes, it is asking your default location, right? You locate the proper location where your file is there. Like I kept everything in the D drive, I think. So I'll go to iFoxing. This is my iFoxing master. Okay. So I select this particular folder and I click finish. Because path is very much important when it is asking that module.info file already using SRS. Do you want to overwrite it? Okay, let us overwrite. Let us see. Path is very much important in every case. Otherwise, you will face some problem. Yeah, now it is created, right? So what we can do next? There is a folder called as org.fog.gy example. Yes, you can notice here, right? GY example. You have to expand this particular file. Yeah. Then you can get that fog GUI.java. You have to run it as a Java application. Run as Java application. So if it is successful, then you are able to get this particular tool dashboard. So this is the dashboard which shows two button, that is view and graph. Just a minute. Yeah. It is showing a fog topology creator. You can create the fog topology, as I said, that there are three different layers. One is IoT, another is fog, another is cloud, right? So you have to deal with the three different layers. So in order to create a topology, just you have to drag and drop. There is no need to write any code here. Just like cloud analysis, you are not writing any code. Here also there is no need to write. For example, I want to take cloud. Okay, it is asking what is the name. I'm writing cloud. Let's say it is in level number 1. Okay. Uh, then uplink, I'm giving uplink bandwidth as well as, let's say, downlink bandwidth, and some MIPS, let's say 4096. RAM is, let's say, 1024. Rate MIPS is, let's say, 100, something like that, some random value I'm giving. So you can see here one cloud is created, right? That is in layer number 1. Then if you want to create a fog device, right? You can select it, then you can write, I want to create a gateway 0. Gateway is a fog device, right? So in the level number 2, some uplink and downlink you can provide based upon the requirement. MIPS you have to provide. RAM also, let's say 512, something like that, I'm writing, and 256 some space. So now a gateway is created here, right? And you can see in this console also, you can look into their coordinates, their capability, whatever we are giving input, that is going to be added. Now, if you want to add more gateway, also you can do it. Like I can write gateway 1 in level number 2. Uplink is, let's say, some random value I'm writing. Downlink also some random value. Okay. RAM size also I'm writing, some MIPS value I'm writing. I press OK. So two gateways created, right? Now your cloud layer you have created, fog layer you have created. Now you know you can add as many number of sensors possible. Suppose I want to add a sensor. Let's say it is a SpO2 sensor, right? Okay, it is asking which sensor. I want to say SpO2. There are different type of distribution you can use here, like normal distribution. You have to mention the mean and standard deviations. Uniform distribution, you have to mention the minimum and maximum value. And deterministic, you have to give the value. For example, I want to go for uniform distribution. I am mentioning 100 and maximum value is 1000, right? So you can see one SpO2 sensor I have added here. Let's say I am adding another sensor. Let it be a blood pressure sensor. I'm writing BP. And the distribution type is, let's say, normal distribution. I am saying mean is 10 and the standard deviation is, let's say, 5. So I've created another sensor here, right? And you know the difference between sensor and actuator. So like you can consider a agriculture field where we have deployed some kind of a sensor, and actuator is nothing but the motor. Okay, when a agriculture field needs requires some water, then sensor is providing a reading, right? By looking into reading, you can instruct the actuator, or that like a pump or a motor, to uh, provide the water to that particular land. So if you want to add actuator, this is the actuator symbol you can add. I'm writing, let's say, actuator SE-0. Actuator type is SE-0 only. So one actuator is added now. I want to add another actuator, let's say SE-1, and you can go for actuator type. I'm writing the same thing, SE-1. So I've created two actuators. Now what you have to do, you have to connect these components. So in order to connect these components, you can use this wired symbol, right? There is a LAN cable symbol, right? So for example, I am going to say cloud is connected to gateway 0 with a latency, let's say 150 millisecond or something like that. So they are connected to each other. Similarly, cloud is connected to gateway 1 with latency 200 millisecond. So they are connected each other. Similarly, gateway, okay, gateway 0, I'm saying gateway 0 is connected to, let's say, actuator 1. So actuator 0, okay, with some latency of 25. So they are connected. Similarly, gateway 0 is connected to, I can say, SpO2 sensor, okay, with some latency, let's say 50. So you can see there is a connection. Then similarly, I want to add gateway 1 to my blood pressure sensor. So I'm writing it is 335, something like that. And I am also want to connect gateway 1 to actuator 1 with some latency, let's say 350, something like that. Okay. So you can see now I have drawn a topology, my own topology using the fog topology generator. And you can save this fog topology in your local drive. For example, I want to store here as NITW. You can save it, and you will later you can open it. And also there are some predefined physical topologies are also there. If you go to that SRC folder, for example, you can go to my D drive where my SRC, the source file is there, iFoxim. This is iFoxim master topologies, and you can see these are the different predefined topologies that are there in the iFoxim simulator. For example, I am going for vrgame.topo. So you can see this is the example of this topology where we have sensors and actuator in the bottom layer, and we have fog layers here. And these fog, two-level fog layer, one fog layer is this one, another fog layer is here. Then they are connected to the cloud through a proxy server. So like that, you can create your own topology. You can use other topology, and whatever topology you are using, you can see which one is the start node, target node, how the communication actually happens between these units. That is also shown in the console. Right. So I'll share these things with you. I request all of you to go through these materials to explore the fog computing and its a simulator. Okay, let us stop here. If you have any question, you can ask.